So here, once again, I see I'm dealing with an acid solution. Remember, the first question I want to ask is, am I dealing with a strong acid or a weak acid? So HCN is on my list of weak acids. Also, I've given you a Ka, so I know HCN is a weak acid. The next question I ask myself is, am I reacting it with a strong base? Am I doing a titration? So here the answer is no. I'm saying what's the pH of a 2.0 molar solution of HCN? So I don't have to convert to moles. I'm not doing a neutralization reaction. I don't need the Henderson-Hasselbalch equation. So with this is kind of our fundamental equilibrium that we get with weak acids. So we need to include the fact that our weak acid only disassociates slightly. So only a very small amount of my HCN is going to disassociate to make hydronium. So we set it up. We set up our Ka reaction. Our weak acid plus water goes to make its conjugate base. So the conjugate base means I've lost a hydrogen here. And then because we're talking about a Ka reaction, we know we're making hydronium. We know we're starting with a 2.0 molar solution. And I know that some of this is going to disassociate. So we understand this equilibrium will go to the right. When we start out, we don't have any Cn minus, we don't have any hydronium. So we understand this reaction needs to go to the right. By how far? X. So we're assuming of my 2.0 molar, some amount of it is going to disassociate X. And because it's a 1-to-1 mole ratio for every X amount of HCN we break up, we make X amount of Cn minus and X amount of hydronium. I then come up with my equilibrium expression for my Ka. So it's products divided by reactants. Water doesn't make it into that. That's going to be equal to my Ka constant. I then take these equilibrium, this algebraic expression that we came up with here and plug them into my equilibrium expression. So X for Cn minus goes in, X for hydronium, 2.0 minus X goes in for HCN, and that's going to be equal to my Ka. So to avoid the quadratic equation, we are going to go ahead and assume X is small compared to 2.0. And when we have that, now we can simply solve for this X value. So we assumed X was small, so we got rid of this. Now all we have is to solve for this X value. So I multiply across, so I multiply both sides by 2. I combine these two X's together to get X squared. And then I multiply these two numbers together and take the square root of both sides to get X. And then remember, we've decided that X, once we find it, is equal to the concentration of hydronium here. That's going to be equal to 3.5 times 10 to the minus fifth. So now that I have my concentration of hydronium, I want to find the pH. pH is equal to the negative log of the concentration of hydronium. We've found the concentration of hydronium. And I'm sorry, this should be a 3 right there, but the answer is correct, 4.5, and I'll correct that in the answer key, but this should be 3.5 times 10 to the minus fifth, but our answer is a pH of 4.5. So no, this is another classic one. I ask you for the pH of a 0.2 molar solution of nitric acid. So same thing, first thing I want to understand is this a strong or a weak acid? And I know nitric acid is on my list of strong acids. Another dead giveaway is I've not given you any Ka information. So here I understand because nitric acid is a strong acid, there's going to be 100% dissociation. So even though we can draw out this reaction, we understand that the equilibrium is going to be all the way to the right. So we don't need to do any calculations involving the K value. What I do understand is that when we look at this dissociation, because it's going to be going all the way to the right, for every 1 mole of nitric acid we put in, we're going to get 1 mole of hydronium out. So there's a 1-to-1 mole ratio here. So I've given you the molarity of nitric acid. What we want is the molarity of hydronium. Well, it's a 1-to-1 mole ratio. I'm putting in 0.2 molar of nitric acid. That's going to completely disassociate to make hydronium. So I'm making 0.2 molar of my hydronium. In this case, all I have to do is take the negative log of that concentration of hydronium. So we want to find the pH. That's equal to the negative log of the concentration of hydronium. That was given in the original question here. We just needed to realize that these two numbers are the same. I take the negative log of 0.20, I get a pH of 0.7.